Hi, class. This is Mr. Krieger. This is geometry. We're starting Unit 9. This is Lesson 1, the special right triangle, so please print up the lesson. Before we get started on the lesson, though, I want to show you something that's going to be useful not only for our present lesson, but also for trigonometry. And here's the idea. If I start out with a triangle where I know this angle measure, and I actually measured this angle with a protractor, and let's say I'm going to actually create the sides of this triangle using pieces of straw. What I want you to notice, and this is not going to come as a surprise to you considering what we learned in the last unit, if we were to double this side, then really every side should double. Now this piece here, you should be able to construct that third piece using two of these, meaning it's doubled. And so it goes to show that if the angle measure here is fixed, then you could scale up this triangle any amount. It could be double, triple, or even 1.5 times. And you're going to be able to know what the relationship between all the sides is. And that's basically the whole principle behind trigonometry. And one of the nice things is there are some particular relationships with some angles, like in the case of the 30-degree angle, where we don't even need trigonometry to do work. And that's what we're going to take a look at in this lesson. So here's the first thing I want you to look at. We're going to look at a special type of right triangle. It's called the 30, 60, 90 right triangle, right? How you find this right triangle is by taking an equilateral triangle. Now, do you remember what the angle measures are for each angle? They have to be equal because it's equilateral, so all sides are equal, all angles have to be equal. So 180 divided by 3 is 60. Each of these angles have to be 60 degrees. Now we're going to draw an altitude to the base. Now you know when you draw an altitude it makes right angles there, right? Okay, why does it bisect the base? Now we know this is 2, but how do we know those are 1 point each? I mean 1 unit each. Well, the fact is that we know this angle has to be equal to this angle because they're both 60 degrees. These are two right angles, and you have a reflexive property here. So by the left triangle and the right triangle are going to be congruent by angle, angle, side. Okay? Then we're going to know that this piece, this piece and this piece have to be equal by corresponding parts of congruent triangles are congruent. Remember C, P, C, T, C? So therefore we know these are both 1, right? Now, one thing we want to know is we want to know how long this side is. So let's try to figure that out. Well, if we take a look at only one of the sides of the triangle, it's a right triangle. This side is 1, this side is 2. This is the altitude, and we could use the Pythagorean theorem. A squared plus b squared equals c squared. So plugging in what we know, this is the hypotenuse. 1 squared plus x squared equals 2 squared. 1 plus x squared equals 4. Subtract 1 from both sides. We get x squared equals 3. So we know the altitude of this triangle is the square root of 3, right? And what do you think this angle up here is going to be? Well, we know this angle here is 60 degrees. We know that all these angles were 60, right? 60, 90, well, that's got to be 30. So that's a 30-degree angle in that corner up there, okay? So, right, you can figure that out just because if 60 plus 90 is 150, subtracted from 180, that has to be 30. And now we have this thing that we call the special right triangle, the 30, 60, 90 triangle, right? Now here's a couple of things you should know. First of all, the right angle is here. Let's call this the 60-degree angle. This has to be the 30-degree angle. And you know, we just learned the sides. This is 1, 2. This side is the square root of 3. Now, you got to put these numbers in the appropriate spots. And the way you know is that the 1 is going to be across from the 30, the 2 is going to be across from the 90, and the rad 3 is going to be across from the 60, and that's because the smallest angle goes across from the smallest side. The idea is that as an angle gets smaller, the side across from it gets smaller, so the small angle goes with the small side, and the big angle goes with the big side. And rad 3 happens to be approximately 1.7. Okay, so this is actually in the middle. Smallest side, smallest angle. Biggest side, biggest angle. Medium side, medium angle. Just remember this. It's as easy as 1, 2, rad 3, where the rad 3 grows across from the 60. So let's see how we could use this idea to scale it up. Remember I showed you the example with the straws, how you can scale something up? Suppose this side happens to be 8, and we know it's a 30, 60, 90 triangle, right? Well, then every side of this triangle has to be 8 times as big as that. So this side here is going to be 2 times 8, which is 16. This side is going to be 16. This side here, we're not going to use this. We're going to use the radical. But 8 times the square root of 3, actually the way you multiply it together is just by doing that, 8 rad 3. So there you go. You can scale the sides of the triangle up. If you know the side opposite to 30 is 8, then this side has to be double that. I mean, not double. This side has to be 8 times that side. This side has to be 8 times that side. So 8 times rad 3 is 8 rad 3. All right, let's try some more practice. Okay, so let's take a look what we have here. You could try the next problem on your own. You could pause the video and you could check to see if you got the right answer, okay? So here we see that we have a 30 here, the 90 is here, the 60 is going to be over here, right? I'm going to draw a little model for myself right here. This is the 60, this is the 90. I know the 1 has to go here, the 2 has to go here, the rad 3 has to go here. This is 5 times as big as that, so this has to be 5 times as big as that. 2 times 5 is 10, that side must be 10. Multiplying this by 5, because this is 5 times as big as that, we're going to get 5 rad 3 on this side. And we found, and the scale factor was 5. Okay? Now, this one, let's take a look. This is the 60-degree angle, this is the 30-degree angle. Let me draw a little model for myself over here. I know that in my 30, 60, 90 triangle, the 1 has to go here, the 2 has to go here, and the rad 3 has to go here. Well, this is 7 times as big as this. So to get this side, I just have to multiply this by 7. 7 times 1 is 7. And to get this side, I just have to multiply this by 7. Remember, everything here is 7 times as large. So if I multiply the 2 by 7, I know this side is 14. Okay? Try this one out. Okay, remember the 60 is over here. Let's draw a little model over here for ourselves. Here's the 60. Here's the 30. We know the 1 should go here, the 2 should go here, and the rad 3 should go here. So let's see how many times bigger that is. This was 6 times bigger. We have to multiply everything by 6, so it's a scale factor of 6. Okay? So 1 times 6 is 6. This side is going to be 6. Rad 3 times 6 is going to be 6 rad 3. That's how we get this side right here. Okay, let's try a similar example to the original problem. If you remember, we started off with an equilateral triangle. If the length of each side of an equilateral triangle is 8, what's the length of the altitude? Well, we know that this equilateral triangle breaks up into the 60-degree angle here, 30-degree angle there, 90-degree angle there. Let me draw a little model for myself. Let's do the 30 here and the 60 here. So this would be 4, right? And 4, I'm sorry, here we want to put, if this is the 60-degree angle, we want to put the rad 3 here, the 2 here, and the 1 here. So this is 4 times as large, so the scale factor is 4. We want the altitude, which is right here, it has to be 4 times as large as this, so therefore the altitude has to be 4 rad 3. Okay, because it's a scale factor of 4. Okay, let's take a look at the next thing. We're going to take a look at one other special kind of right triangle. Remember, these are all special right triangles. This is called the 45, 45, 90 right triangle. Let me show you how you would create it. You start off with a square with all equal sides of 1, right? Now, suppose we were to draw in a diagonal. What are the measures of angle A and B? Well, we know that when you draw in a diagonal of a square, it bisects the angles. It cuts those angles in half, so those angles would have to be 45 degrees each. Now, we want to find the length of that diagonal. So what I'm going to do is I'm going to draw a right angle here. This is 45, 45, 1 and 1. And how are we going to find this side? Well, you know, it's a right triangle, so you could do a squared plus b squared equals c squared. Plugging in what we know, 1 squared plus 1 squared equals x squared. 1 plus 1 equals x squared. 2 equals x squared. X squared equals 2, square root both sides. We get that that is square root of 2. So x is the square root of 2 is the length of the hypotenuse there, right? So here is the basic 45, 45, 90 right triangle. 1, 1 rad 2. That's what it's going to look like. So you need to remember for a 45, 45, 90 triangle, the sides are 1, 1, rad 2. Rad 2 is the longest side. Square root of 2 is actually, let's figure it out. What is the square root of 2? Square root of 2 is 1.414. So that's the longest side. It has to be the hypotenuse. It's isosceles, so these are the two equal sides. And now the scaling process works similar to the one with the 30, 60, 90 triangle, except we're going to use these as the new sides. So let's try this problem out. We want to find the missing sides here. Let's see how many times bigger this triangle is from our original triangle. Well, 6 rad 2 is 6 times as big as that, which means the scale factor was 6. 6 times 1 is 6, so this side is 6. It's isosceles, so these two sides both have to be 6. All right, let's check out this problem. All right, so how many times bigger is this side compared to that? It's 9 times bigger. Isosceles triangle, this has got to be 9. This has to be 9 times bigger than that. 9 times radical 2 is 9 radical 2. And that's how you find the missing sides of this special right triangle. Okay, last page. Here are some harder examples that are going to require a little more work, but you have the tools to do this. Let's take a look. Let's find the missing sides of this triangle, right? Now, if you draw your model, which is always what I like to do, draw your model. You know the model has the sides you know, 1, 1, and rad 2. When you look at this side, you're like confused. Like, isn't there supposed to be a radical on this side? Well, the model has the radical, and it's nice when there's a radical on this side, but it doesn't have to be. What's stopping this side from being a whole number? Nothing, right? But then again, if we have this is our model, how are we supposed to figure out what x and y are? What you do is, these triangles are similar. Set up a proportion. How are we going to do this? Well, let's say we want to find x. Let's start with x. And we know 10, and we know this side, and this is like our x. So let's make a proportion with x and 1, 10 and rad 2. So let's do that. So we're going to get x is to 1 as 10 is to rad 2. Cross multiply this. Now I want to get x by itself, so I'm going to divide by the square root of 2. So now I have 10 over the square root of 2. Now, I don't know if you remember how to do this, but this is actually the answer for that side, but we usually like to rationalize the denominator. To rationalize the denominator, we multiply by rad 2 over rad 2. This is going to become 10 rad 2 over rad 4, which I'll work up here. So that's going to be 10 rad 2 over the square root of 4 is 2. I can actually divide these numbers, so we get 5 rad 2 is the length of this side. And what makes this so easy is this is an isosceles triangle, so if this is 5 rad 2, this side also has to be 5 rad 2. So if you ever come across an example where it's like, well, that doesn't look like what I'm used to, make a proportion. These triangles are similar. Just make the proportion for the sides that are corresponding to each other. So here's another problem similar to the one we just did. So let's take a look. Let's make this is going to be the 30, 60, 90 triangle. And we know in our model that across from the 90 is 2, Across from the 60 is rad 3, and the 30 is up there. This should be a 1. So again, this is kind of defying our expectations. We're used to seeing a radical on this side, and there's no radical there. But that's okay. Let's try to find x first. Let's just make a proportion because we know similar triangles. We'll match up these sides and these sides. We'll ignore the y for now, because if we use the 12, the rad 3, the 1, and the x, there's only one variable, so we can actually set that proportion up. Let's do that. So let's do x is to 1 as 12 is to rad 3. X over 1, 12 over rad 3. Cross multiply, we get x rad 3 equals 12. Divide both sides by rad 3. So we get x equals 12 over rad 3. Now, just like before, we like to rationalize our denominator. So to do that, we multiply the top and bottom by rad 3. So you get 12 rad 3 over square root of 3 times square root of 3 is the square root of 9, which just happens to be 3, right? You could try that out for yourself. And now we can divide that. 12 divided by 3 is 4. So this side is 4 rad 3. That's our x side, 4 rad 3. Okay? Now you could do a similar process to find this missing side, but one thing that makes this one a little easier to find this side is to note that this side compared to this side is just double. So we really just need to double this side to get y. And to double 4 rad 3 becomes 8 rad 3. That means this side is 8 rad 3. So what y is 8 rad 3. Okay, so that's how you do that problem. So please make sure you understand this. This is going to be an important topic for Algebra 2.